Yo, what's up, what's up? Welcome back. Today we're working on my operating system written in Rust for targeting like x86 platforms right now. What it does right now is like it boots, it has like memory allocation, it has like Rust async support, it can like log to like the terminal, it can log to like the VGA window, it has like clock support, so we can do sync sleep, so we can do things based off time, we can like set the time, we can and we can like work with the internet a little bit. So if I like try to like connect to my thing over TCP and I like send it something, it'll send it back. So we've got like some form of like network support. What I want to do today is I wanted to try to like draw something to the screen. So right now we have the like logs come out over serial, which when we launch our operating system in a virtual machine, it like takes the serial output and pipes it into my terminal so that we can see here. And we're also logging to like the monitor, quote unquote. And so this is showing like what our OS would show if we were running on actual hardware and our OS like was functional on actual hardware, which I bet it is not at this point. But this is like screen, this is console. And I think at this point in time, we don't really need the logs duplicated on the screen. And it would be fun to be able to draw something interesting here. So what I was thinking was we would see if we could like initialize a frame buffer. And from there, what does it look like to actually draw something and to like maybe draw something interesting. And if we get that working, we can start working towards something like some sort of game or something fun like that. Yes, that's what I want to do today. So that's intro 155. Okay. So how does this work? There's this thing called the frame buffer. And I actually don't really know what it is. I know that it's like you write to some video memory and that just shows up on the screen, but I don't really know like who implements it. Let's see if we can figure that out. Frame buffer. Portion of memory containing bitmap that derives a video display. It is memory buffer containing data representing the pixels in a complete video frame. Modern video cards contain frame buffer circuitry in their cores. Sure. So I don't really know how we like get a handle to this. I know that the BIOS can tell us where it is, and I know that grub can set up for us. Like it can like initialize it and pass that info onto our operating system. But I don't really know what it is in hardware. And that's okay. I can kind of like ignore that for now. We'll just kind of say like, okay, somebody is providing us video memory and we can just write to it. And so the first thing that I have to do is I have to ask the bootloader, instead of giving us, where is it? This guy, a place where we can like basically just write text to and it'll render it. What we want instead is we want the ability to draw. And so we have to ask the bootloader to give that to us. And the way we like request stuff from the bootloader is we like inject some code into the front of our binary. Well, code. We inject some like data into the front of our binary. So let's just pull open some diagrams. So at the start is probably maybe not true. I don't really quite remember. So like this is our binary. Kernel. Somewhere in here, we kind of like chunk out some stuff towards the beginning. In here. Right? And what happens is the bootloader, it like opens up our hard drive or a CD-ROM or whatever, and it starts like scanning. It goes like, well, is there anything interesting in here? He like walks along the top of it, and he sees like, ooh, there's like a special number here that means that like I should use this data in here to look at something interesting, or to like determine how I'm going to launch a kernel. And the way we define that right now is in our bootloader, we just kind of define these manually in assembly. So we say like, at this section, multi-boot, we declare like a section. We say, here are just some numbers. Here's your multi-boot magic. Here's the flags that we want for you to initialize this with. And here's a checksum, which is important because if it sees like this magic number but it doesn't see this checksum, that means that like it's found that number by mistake, and we need to make sure that it knows that, like, no, we're intentionally, this really is a multi-boot thing. Yeah, so here what we're requesting right now is we're requesting some like we're requesting to put us in memory in like an aligned way, and we're giving it we're asking it to like provide us information about like memory of the system. And what we can do is we can also ask it to provide us video memory. So here, if bit 2 of the flags were to set, information about the video mode must be available to the kernel. And here, if we set flags bit 2, we can request a buffer that has like a specific width, height, and color depth, as well as we can ask it to be in text mode or in text mode or draw like frame buffer mode or something. Let's see what it says. EGA for 1 for EGA standard text mode, 0 for linear graphics mode. So that's what we want to set. And so I think what we can do is we can just look at this header and say, well, the flags we're already injecting, and we just need to set the bit 2 of flags. So we'll say set, let's see, what did they call it here? Video, I guess. Which is going to be 1 shifted to the left 2, because we're going to want to set the second bit. And the flags now will just include video. And now everything else still works the same. Our checksum is still correct. But now we need to provide this stuff down here. So let's see, how do I want to do this? So right now we're dropping some numbers in like this. We've got long, magic, flags, checksum, which apparently are 4 bytes each. Long, GCC ASM. What does it mean? Dot long. I don't know how to like find these documentations. Let's see, man GCC, no, man AS, man, isn't AS the assembler? GCC assembly reference. Let's see, dot long, dot in, nope. Dot long. It's weird that I don't see this anywhere when I search it. Okay, that's okay. We can infer from the fact that we've used these for the other 4-byte variables that this is 4 bytes each, which means that when we get down to byte 32, we should be also using long to set the mode type, width, height, depth, because each of these are 4 as well. So I think what we're going to do is we want to skip 32 minus 12, right? Because we don't want to set any of this stuff. And this is at offset 12, and this is at offset 32, so we just skip that many bytes. It would be so nice if I had, like, is skip defined in here anywhere? GCC, or, new assembler skip. Like, somebody has to... Aha! This is what I was looking for. Okay, so long is the same as int. Int is, byte order and bit size number depends on what target assembly is for. Okay, that makes sense. And then here we have skip, which is in size, and we can fill it if we want. Okay, so we've skipped a bunch. And now I want to set the mode type. So here, they said that if we want text mode, we should put 1. Otherwise, we should put 0. So let's start with putting 1 and just kind of see how that works. And then we'll set like width is 640, height is 480, and depth, oops, these are longs. And the depth should be 0. We don't really care for now, and we'll just see what they give us. So if I cargo run this, let's see if I change the resolution here. What is it, 1024 by 768? Is that a normal resolution? We don't see any difference. But what if we put this into the other mode? Oh, oops. He's been complaining to me. Multiboot knows VBE, but we do not. Okay. So let's see what that means. QEMU multiboot knows VBE, but we do not. What does that mean? QEMU doesn't support VBE. You need to use grub. VGA. QEMU with VGA SDD does support VBE. It just won't initialize it for you like grub. Okay. So we need to load it through grub. Luckily, we have support for that. We did that in the first stream here. Is that we started by running with a ISO that we like injected grub into, and that loaded our kernel. But then we switched to using this like dash kernel argument. Where is it? Hello? Here. We switched to using this kernel argument that says like, hey, QEMU, could you boot the kernel for us directly? Because we didn't see any difference between doing it that way and this way. But that's clearly not right. So, it was right, but that's not good enough for us anymore. So what we want to do is we want to change this to boot using grub. So what we have here is we have like a build script. And this should set up the ISO to be loaded. Like that should build us an ISO that contains our kernel. So let's just double check. How do I make sure this is working right? Why is this like, when I cat stuff, it doesn't seem to know, it's not like printing the whole line. It's doing something stupid with like chopping off the end of the line. That's fucking annoying. Okay. But if I run this QEMU command, but instead of kernel, I think it's cd-rom my OS ISO. Could not configure netdev. Oh, because all of these things aren't set. Fuck. Okay, so what I'll do instead is I'll just edit this script. And I'll say cd-rom myos.iso. And then run QEMU wrapper. Okay, so here we go. This is now loading through grub. And if I set this to mode 0. Oh, oops, I have to build it first. This is giving us like a 1024 by 768 window that's all black. Okay. So that's kind of nice. We have to think just a little bit about how do we set this up so that we can automatically get this running correctly. So in our build script, we have this like ISO creation stuff. And probably what we can do is we can just probably put this in the wrapper script. So we have kernel is the first argument that cargo is giving to us. We can do all this stuff where we create the ISO. And then we run it. And yeah, that seems reasonable. So here, instead of target debug kernel, we just say kernel. Okay. And now if I cargo run. Okay, so that boots my kernel. And if I run cargo test, do the tests still run? Yeah, they still run. Okay, so the only problem now is that my grub is like taking time to launch, and that's gonna fucking annoy me. So I think that there's like a way to set the timeout. Grub config timeout. There's a way to just make it like immediately boot. Timeout variable is set. Okay, how do I set environment variables? Environment block. Environment block is a something. pre-allocated byte file. That doesn't seem right. Grub config set timeout. What's this guy doing? Come on, why can't I load this? That's annoying. Oh, here we go. This guy's saying set timeout. Just raw, okay? So let's say set timeout equals 0. Do I need to put a semicolon or anything? No, looks good. So now I have cargo run to relaunch with the new parameters. And that does boot much faster. Okay, that's cool. Cool. Okay, so maybe I set this stuff to not output, just to like clean up the output a little bit. That wasn't right. Maybe I need to do standard error goes out. There we go. Okay. So that's all working nicely now, and I think that's like a good checkpoint. So here we'll say git commit, and we'll say initialize framebuffer instead of text mode. Update the multi-boot params, the multi-boot header to request linear graphics mode, I think is what they called it. Update QEMU wrapper script to use grub to initialize because QEMU kernel mode does not support framebuffer VBE is what they called it. Okay, cool. So now we've got this like frame buffer that we can work with. And now what we have to do is we have to start actually parsing the data that comes from grub that will tell us where we can write to. Okay. So I guess we're going to hope that flags 12 is set, and then we can start working with the frame buffer. So in main, what do we do here? We get in this like multi-boot structure from them on boot. So there's like a kernel main that we call, and here we have like a multi-boot info. And in here, we've punched in everything down to APM table. And I guess we can just punch in these guys as well. So these guys are all of these 4 bytes. 4, 4, 4, 2. 2, 2. Oh, that's annoying. That's annoying. Whereas like maybe I think there's like a multi-boot header I can just copy paste from. Where here we go. So we can just copy this stuff and adjust as needed. Okay. So it's something like this. And we want to, I guess, start search and replacing these. So we're going to say s uint number 0 to 9 star. The reason that I'm doing this is because I want to convert these from like multi-boot uint16t to like u32, u16, u8, etc. And so I'm like capturing that section. We underscore t and multi-boot. Here we go. And we can like replace this with the thing that we found prefixed with a u. I think that's it. Cool. And now we just have to convert these into Rust format. So we delete the thing, we stick it at the end, and we replace the semicolon with a comma. There we go. There we go. Okay. So does that line up with what they told us in this guy? Height, and frame buffer type. and color info. And here, color info is actually going to be a bunch of U8, just like a U8 buffer of length 5, I think. Is that right? Color info? And because it looks like from this header, the color info could be like 2 different types, right? It could be 1, 2, 3, 4, 5, 6 UID dates, or it could be a palette, which makes sense, I guess. So either we have like, oh, there's a blue over here, I'm gonna use that blue, or we can stick in like RGB, I guess. Okay, and it looks like it's based off of here is what type we're gonna get from it. So that makes sense. And so what we're gonna have to do is this is actually gonna be like an enum, probably. It's easier for me to manually cast the buffer to like the different types depending on which one it is. So we'll figure that out later. So the first thing that we want to do is once we've got the frame buffer in from multi-boot, we want to see if flags 12 or 11 are set, because we expect those to be set now that we've asked the multi-boot. We've asked the like grub to give that to us. So if we say for now, how do we want to do this? Somewhere here we turn this into, we get the multi-boot stuff. And I guess we can just say, we can just make a function that's like print stuff for now, right? I just want to like have a way to debug what we get, and here we'll just say, where do we want to print this stuff? Probably just at the front of main, or I guess after kernel init. So we'll just say info.print stuff. Okay, so in here, let's print out self dot flags as a I guess we want to see the specific bits. So we want to see if bit 12 is set and bit 13 is set. We need to use our like utility type for bit manipulation get bits, which essentially just does like shifting and masking for us, right? If we look at like the implementation here, we just do shift and mask by like some, depending on like how many bits we want to get at once, etc. Okay, so this is supposedly packed, but I actually don't think it needs to be, so let's just do like unpack it, because I think that everything will be aligned anyways. And let's cargo run and see if we get stuff printed. So we have true and false. So bit 12 is set and 13 is not. But there is no bit 13, so that makes sense. We actually want to check 11 and 12. And both 11 and 12 are set. So I don't actually know what VBE is, but I suspect that it doesn't matter. Right? I suspect that if we just start writing stuff into the frame buffer, we don't need to look at this. But maybe we can read something down here and they'll tell us what VBE is. Protected mode interface defined by VBE 2.0. This information is not available as fields contain 0. Note that VBE 3.0 defines another protected mode interface, which is incompatible with the old one. So what the fuck is VBE? The fields VBE control info and VBE mode info contain physical addresses of VBE control information returned by the VBE function 00h and VBE mode for which. Okay, sure. What is VBE? And the other thing was talking about frame buffer table contains the frame buffer physical address. This field is a 64-bit wide, but the bit loader should set it under 44 gigs, etc., etc. Okay, so if it's sure, there's like these 2 different color types. Okay. Well, let's see what VBE is. VBE BIOS. What the fuck is a VESA standard? But what's a VESA? Video Electronic Standards Association. Sure. So basically, okay. Sure. So it's just like a set of standards that all BIOS manufacturers, I guess, implement. Sure. So there's page flipping. That's nice. High color and true color. Okay. Oh, nice. 16 and 24-bit graphics. Okay. Interesting. So maybe this guy will tell us, where is it? VBE mode. Maybe this will tell us like information about it. About like what type of graphics stuff we support, I guess. And in here, maybe they had some like VBE flags. I think generally I don't care right now. That's my guess. My guess is that we can just look at the frame buffer address and start working with it. So let's look at that. So we have frame buffer adder. Let's see what that is. Frame buffer adder is self frame buffer adder. Cargo check. Cargo run. So we do get an address. And maybe we should look at the pitch, width, and height. Because that will give us an indication of if the data is sane. Okay, so let's look at that. So we do have 1024 by 768, which is what we requested, right, in our assembly file. And like if I do 640 by 480, do we get that as well? Okay, so that's a really good sign that what we're parsing is correct. We're getting back exactly what we asked for. And so we can probably assume that the address is right as well. BPP, I assume, stands for bits per pixel, which will tell us, it'll inform us of like how much we should offset, probably, per pixel. So let's look at what that is. And let's, while we're here, print out the type as well. Okay. So we have 32 bits per pixel, frame buffer type 1. Which, if I remember correctly, is just we're allowed to do, like, it's the second one where we have red, green, blue directly. Okay. So let's try to maybe just put anything on here. And then we'll have a good idea of if it works correctly. So we'll say for pixel in self.framebuffer pitch. I guess it's for row in frame buffer pitch, that's column. And so we have for row in self.framebuffer height. Right, so we'll iterate over each row, and within each row we'll iterate over each column. Now, pitch is close to width, but it's not exactly the same. So we actually might be in a situation. Yo, what's up? We're working on graphics initialization in our operating system. So yeah, what we're looking at is we've got this like pitch and height variables, and pitch and width are not necessarily the same. So often what happens is they want like each row of pixels to be aligned with something. So if I've asked for a width of like 1024, they might actually just like add some like garbage buffer over here that like isn't anything of value, but just so that like these points are aligned in memory in a way they want. So we have to iterate over pitch. I guess we actually want to iterate over width. And we'll go column by column, and we'll say that the address that we're trying to write to is going to be the frame buffer address and this is going to be plus some offset. So we'll calculate the offset first. The offset is going to be the row times frame buffer pitch, right? Because we're saying like if we're at row like 4, we're going to have to jump pitch to 1, 2, 3, 4 times, and then plus the offset in columns. And so then this address that we're going to try to write to is the frame buffer address plus the offset. Okay. And this frame buffer adder is going to be a U8 pointer, I guess. And this offset actually has to be multiplied by the bits per pixel, if we are correct about what this BPP stands for, I assume, but I didn't actually check. Or maybe it's either bits or bytes. So if it's bits, we have to divide by 8, and if it's bytes, we cannot. Given that it's 32, that's probably bits. So let's just divide by 8 as well. Cannot multiply U32 by U8, so we'll do this as U32. And these should actually all be U sizes, not U32s. Because we are working... U32 is fine. U32 and U size are actually equivalent in x86, but fuck it. Doesn't matter. Okay, so now what we want to do is let's first see what is currently in there. So we can probably guess that they're going to be all zeros. But maybe not. So if we go over each pixel and we print them all out, they are all zeros. So let's just do like the stupid thing and set them to, we'll write volatile because this is like hardware memory mapped. I'm not really convinced that just writing to the memory will do what we want. Rust might like optimize some stuff out. So we say, hey, like just so you know, like something else that's not you might be touching this memory. And let's just set it to like all whites. And let's see if that actually like gives us something interesting on the screen. Okay, so that's interesting. So we do, in fact, see all blue. And let's just see if we only do the left half of the screen. Do we only see blue on the left half of the screen? Okay, that's a really good sign. That's a really good sign. So that means that we understand our frame buffer to some extent. I don't know why it's blue, right? I would have thought that if I wrote FFs everywhere, that'd be white. Oh. But it's because I'm only writing the first of the 4 bytes. So if we did this, adder as mute U32, and we wrote 32 bits of data instead. Here we should get it as white. So what I've done here is I've said like write basically all ones to this area of memory. And it's white now. Okay, that's really good. There's also something going on where there's like scan lines. That's kind of odd to me. But we can I'll think about that maybe after. I think this is like a reasonable target that we've like said we've initialized the frame buffer. So we'll say that took like 34 minutes-ish. And now let's try to like really understand like how we're supposed to write like colors and stuff into here. So we'll say that we want to parse coloring info, right? Because this guy is basically telling us that he might be giving us palettes, or he might be giving us this like RGB position mask size stuff. And so maybe it's worth looking at that. So let's look at the frame buffer type. This thing for print stuff, this is no longer true. We're not printing stuff. So let's just say initialize frame buffer. And I think in main we might have to write this as well. Yep. Okay. And what are we going to do? We're going to parse the color info. So we'll say match self.framebuffer type. And if it's, what are the options here? We have 0, 1, or 2. So 0 is going to parse the colors as palette. So we'll say initialize palette frame buffer, maybe. Right? We can imagine that depending on if we're working with a palette or RGB, our implementation of the frame buffer is probably going to be like almost completely different, right? Because if I were to write, if we have like a palette of colors, hold on, we'll draw it. Say I have like a palette of colors over here where I have like, you know, I guess I'll just draw them like pink, and then I have like blue, and then I have like green. Oops. My implementation of my frame buffer is probably going to be something like, if I want like pink, I'll write like a 1 here. And if I want green, I'll write like a 3 here, or 2 here, sorry. And if I want blue, I'll write like a, oopsies, pink I want like a 0, and if I want green, I want like a 2, and if I want blue, I want a 1, right? So I'm going to like go pixel by pixel and write the index into the palette that I'm using. I'm assuming, I don't actually know that, I'm just guessing. And if I've got like the RGB thing, I'm actually going to have like wider pixels, and I'm going to write the raw RGB values in here. I'm going to write like, you know, 2, 55, 10, 10 or something to get like a certain like RGB color, right? And so while both of these frame buffer implementations will share, it will share like some stuff, like offset, like the fact that we're working with a grid of pixels, how we write to each pixel is going to be different. So probably we're going to have like different types that we're going to use to abstract this like writing of pixels. And then we might have like a canvas type that takes in a pixel writer or something. I haven't really thought this all the way through. Also, we're kind of in the state here where we only need to support one mode because Grub is only giving us one mode. I don't know if we can like request a palette mode versus RGB. So maybe for now, to keep things simple, I'll only implement the one that I currently see and just say unsupported, like log an error on the other one. Let's do that. So we know that we're getting type 1. So we'll say if self frame buffer type is not equal to 1, we'll write an error frame buffer type is unsupported. And then we'll pass in self frame buffer type and return. Otherwise, we will assume that we're type 1 and we'll parse the color info. So what does that look like? These are each 1 byte where we have red position, green position, blue position, and size as well. So color info 0. We'll just copy paste this a bunch of times. So this is going to be GB, R, and then this is going to be R size, G size, B size. And then each of these are going to be incremented by 1. And can we print these? So we can say print line 1, 2, 3, 4, 5, 6. And then for each of these, we're going to delete a word and delete the rest. Okay. Then we put a semicolon here and join all these lines. There we go. Okay. So what does that give us? 0, 0. What the fuck? Zeros are crazy. So we have no red? Oh, red position is 0, but red size is 1? That doesn't sound right. Mask size. Green field position, green mask size. Blue field position, blue mask size. That doesn't look right at all. Not right at all. Right, like the fact that this is 16 for 0, 0, 16, 8, 8, 8. Right, so if this is supposed to be position size, position size, position size, this should be 0, 8, 16, 8, 8, 8 or something. If frame buffer type is set to 1, it means direct RGB color type is defined as follows. Maybe I do need this to be packed. Maybe it's like adding some alignment and that's causing problems. Which I think means that we have like issues with packed data. So let's start by just seeing if that fixes anything before trying to patch that up. No, so we still see the same thing where we have 0, 0, 16, 8, 8, 8, 8. And the question is, are we like off by a little bit or not? So this should be offset 110. So let's see if self-color 0 is 110 bytes off the start. So self.color info. I think there's like a core mem offset of. And how does this macro work? We should be able to do our struct. So this is multi-boot info. And we want to know the offset of color info. Okay. And this should be 110. So let's say that the multi-boot or the color info offset is this. Cargo run. Oh my god. We don't have the feature. We'll just enable it for now. And disable it later. Okay, so they do really have a 110 offset, so we're looking at the right place. And I swear, either we can't draw red or it's broken. Right? Those are like the two reasonable options given this. So maybe we can look this up. So frame buffer red mask size 0. This is not great. OS dev frame buffer red mask size 0. Let's see. This looks not what I want. Let's just try, I guess, writing red. And maybe we'll assume. Let me think. So first of all, why are they 32 bits per pixel? Right? If this is RGB, then shouldn't it be 24 bits? I guess maybe 24 bits doesn't line up nicely, so they'd prefer to do aligned access. Number of bits per pixel. Right, like I guess we can prove to ourselves that this is wrong, because if we write red pixels, then we'll know that the mask width is incorrect. So here we have, maybe we want to write like FF0000 and see what that looks like. That's red. If we write 00FF00, we get green. And if we write 0 blue first, we get blue. So, and I guess for sanity, what happens if we write the last one? Probably nothing. Yeah, okay, that makes sense. So then the question becomes like, why the fuck is our red size 0? And it must just be a bug, which is annoying. Red mask size. Well, maybe... Does anybody tell us what these are? Color is equal to... Oh, he's only trying to draw a blue line. So he shifts by the mask size. Oh. Oh, yeah, that should be right. And then he shifts by the blue field position. 1 shifted left by the mask size minus 1. Yeah, I think it's bugged. That's my guess. I don't have like another good answer. I guess another possibility is that we've overwritten this memory somehow. So maybe before we do anything in the kernel, maybe we try to print this as early as we can. Which would be like here. Now the problem is we don't have standard input-output at that point, but we would have it here. So let's see if we see anything different if we try to look at it earlier. No, and that makes sense. I don't see why we would have written that memory. Okay. I think I can't see any reason that I'm doing anything wrong. Yeah, that's really odd. Maybe we'll look up like multi-boot frame buffer mask size wrong. Nope, don't see anything very interesting there. Fuck it. Okay, let's just say that red mask looks wrong, but we'll just continue on for now. So here we kind of parse the color info like by like 4735. And maybe we can try to like start drawing something now. So maybe it's worth like moving this into a frame buffer like utility struct. So we'll say we'll just make it in main for now and we'll move it around later. So here we're gonna have like frame buffer, and it's going to have information about its offsets, or yeah, so we'll say red offset is a U8. Blue offset is also a U8. Green offset is a U8. And we'll just call it color size for now. And we'll just use like a little cheat where we'll set our color size to be the maximum of all three or something. Because we know it's broken. Then we need the address, which is going to be a mute U8, I guess. And or maybe we inject the type here. Let me think. So I was going to say that like if we get a frame buffer that is like 32 bits wide, then if we get a frame buffer that's 32 bits wide, we could construct a frame buffer with like a type 32 bits, but that doesn't work because this is going to be like runtime info, so we can't make that choice unless we like create like a factory that like implements a trait and all of that. It just gets like too complex. Did you forget a repr on your struct? So no, but also I double checked that the offsets, I used like the core mem offset of to check that the positioning of my variables was like the right bytes in the struct, and that lined up. So there's something else going on. that I don't really want to figure out right now. I think there's a good chance that there's like some corrupt memory in there, but I don't really care to figure it out for now. I think if it's like equally likely that there's a bug in like the multi-boot implementation, that seems like equally likely to me. Yeah, no sweat. Okay, so I guess I'll store the address as a U8, and then I'll just have to do some like fancy casting, or like some like intentional. If like color size is greater than 8, I'll just have to do some like extra bit shifting and stuff. Whatever. Okay. So I guess what will our interface look like? We're gonna have a way to create one. And what are we gonna need to create it? We need all of these things. So I guess we just start punching those in here. So that's going to be color size, red offset, blue offset, green offset, and adder. And then that will just be a return of this. Easy. We need to take the types off because this is not a struct declaration anymore. So we just punch these guys in like this. I spelled green offset wrong. And then we're going to have like probably a clear API might make sense if we want to like draw something frame by frame. But we can implement that later. The first thing that we're going to want to do is just like set pixel. And maybe we'll do like RGB values as floats, normalized from 0 to 1, just because that's like easier to work with. And then it will convert those into like the correct RGB values. So we'll say that the color is equal to well, let's think. So we'll say that the color is equal to the color times the color size. And this will have to be as U32 or something. Like, we'll assume that we don't need more than 32 bits per color, but that might be a problem. I guess for now, we'll just assert the color size is less than or equal to 8. And that'll just simplify implementation a lot for us because you don't actually care anymore about managing this like 16-bit red value that we'd have to like shift half of it into an upper byte or whatever. Like we'll just, if you write an assertion, then you don't have to care. Perfect. This needs to take itself by reference. Probably, maybe mutable reference, right? Maybe we want to say that there's only one writer to the frame buffer at a time. That seems pretty reasonable. We do the same thing for G and B. So we'll say actually function convert color goes from the value as an F32 to the value as a U32. And that's just this guy. So this turns into val, this turns into this. We still need this bracket. And we need to pass in self. Okay, so now we say let r is equal to self.convertColor r. We do the same for G and B. Then we say let G. Maybe I'll just assert the color size is 8. Fuck it. That makes my life way easier and is true in our case. Because then we don't have to worry about how do I say this? I guess actually what I care about is that the offsets are 8-byte aligned. So that way I don't have to worry about like shifting within a byte. So I can just say that red offset %8 is equal to 0. And the same for green and blue. Then all I have to do is just assign these to the correct bytes. So we'll say what we need to also take in our width and height, our pitch, width, and height, I should say. And then what? These guys get passed in as well. So we have width is a U32, pitch is a U32, height is a U32. And in our multi-boot info, we already had this like conversion from row and column to place, so. And we actually have to set the row and column as well. So row is going to be a U32, col is going to be a U32. And there we go. So here we have pitch. So our offset is row times pitch plus column times color size times 3. No, bits per pixel. We actually need bit per pixel as well. Bytes per pixel. So we multiply that by bytes per pixel. Now we have our offset into the buffer. And this is no longer called framebuffer, it's just called adder. And this needs to be unsafe. And then we say adder add red offset, which is the red offset. This is going to be equal to the R value. So we're going to write volatile actually. So we don't trust the hardware not to do anything behind our backs. Someone here doesn't like the. There's an invalid type here somewhere. This probably has to be as usize. And this has to be as U8. These actually also have to be U8s here. There's no reason to do this like conversions like that. There we go. Color size, I'm just realizing here, val times color size is going to give us the wrong number, because if color size is 8 bits, then this actually needs to be val times 255. So this is one shifted left by color size minus 1. There we go. That's the max value of an 8-bit thing is 255. Okay, and now we can just do the same thing for our green offset and blue offset. And offsets are little Indian actually, so we have to do. Oh, we might actually be in trouble here, but we'll figure that out later. Okay. So now we're missing a bunch of fields here. We're missing all of these guys. No, just. Oh, sorry, we're not missing all of them. We have them here. We have a width, pitch, height. And we're probably missing bytes per pixel, so put that in here, bytes per pix. Okay, and here we have bytes per pix. And yeah, it's actually looking like we're actually just passing in every single parameter inside as part of the new function, which is like error prone or whatever, but it's fine. We'll leave it for now and we'll deal with the linter problems later. And now we need my kernel is 32-bit, right? Yeah. Why are you asking? Just out of curiosity, or was there something relevant to that I missed? Okay. So my multi-boot info, I'm going to have a function to like request the framebuffer info. I think framebuffer adder is a 64-bit physical adder. Yes, I think I read that somewhere too, but I think that the field is 64-bit wide, but the bootloader should set it under 4 gigabytes if possible for compatibility with. Yeah, so I think that it's allowed. Even, oh yeah, I think I don't have to worry about it for now because it's saying that it has to be under 4 gigs. But you're right to bring it up. That's definitely a concern. I'd need to pad past it though. So pad past what? So I have like a 64-bit address that comes in. It's going to be like 32. It's going to be like under 4 gigs. And so then that I convert that address into like a U8 pointer. And then I don't think that there's any like, it's not like I'm using 64-bit pixels or anything. I don't really, I think I'm missing, like if this is when I cast this, it should just take like the 32 bits that I care about. I think. Right? Because if I truncate the little Indian 64-bit, it just turns into like the 32-bit number. All of the zeros are truncated and it doesn't matter. That's my understanding at least. Okay, so when I'm initializing the frame buffer, I want to like get frame buffer info. Doesn't the rest of the frame buffer parameters that follow that pointer, they'd start another 32 bits down? Oh yeah, sure, but I already have this as flagged as a U64 in my multi-boot info. I did confirm that like the offset of this guy does match the offset I expect, and I did confirm also that like my width and height are what I requested, and that pitch is reasonable, and like bits per pixel and type these all line up. Everything after address lines up, so I don't think there's like an alignment issue in here or anything. Okay, this is gonna return like a frame buffer info that isn't constructed. It doesn't exist yet, so we'll say struct frame buffer info. And we're just going to take all of the things that we asked for our frame buffer and we'll put them in here. And maybe we'll just say that we'll hold the frame buffer info. Which is going to be in multi-boot. So this needs to be public. These need to be public now. And all I have to do is fill this guy out. So what's this guy look like? Where does all this come from? So width should be pretty straightforward. Okay, adder is just self.framebuffer adder as mute u8. Blue, oh, we need to keep this like color. Shit, I actually deleted some stuff that I wanted. Where'd it go? Okay. So I did want this color type validation. Maybe I'll just panic this instead of erroring. Crash my kernel because I'm too lazy to deal with like error handling here. Okay, then I can start returning my frame buffer info. So we'll say the return value is this, and he has an address that is self frame buffer adder as mute u8. He has a color size, which is self.framebuffer. We'll take the max of all of the different color sizes. So here we'll do this. We'll say let color size is U32 max. Is there a way for me to like, I guess I can just say R size dot max B size dot max G size. And we'll put a little comment here saying that the R size looks wrong in our test, so we just assume all will be the same. Maybe an invalid assumption. Okay, so now we can just put the color cells in here. Blue offset is going to be B pause. Red offset is R pause. Green offset is G pause. Bytes per pixel is going to be self.framebuffer BPP divided by 8. And here we actually need to assert that it's byte aligned. So we'll say assert that self.framebuffer BPP %8 is equal to 0. Since our framebuffer implementation requires byte aligned colors. Okay. Okay, so our height is easy. That's the framebuffer height. And width is easy as well. Pitch is easy as well. And that's actually everything. Okay, so now we'll, in our framebuffer implementation, delete all this shit. Since it's all already in a structure, we'll say info is a multi-boot framebuffer info. Here we don't need to assert we should still assert these here. Well, we can actually assert these here. That's fine. So this is R pause, G pause, B pause. And now we just pass in info here. Okay. So now all of these guys need self.info, which is annoying to work with, but no big deal. Okay, so now it should be easy for us to pull this return ret out and construct a frame buffer and start drawing stuff. So kernel main, maybe we'll do this like in the demo. So in our demo function, we can just maybe create our frame buffer, or I guess really this should be part of our kernel. So in initialization, we'll have our frame buffer. He's going to be a frame buffer. We're going to construct him here. So we'll call this get frame buffer info, and we'll say let frame buffer is equal to frame buffer new, and we initialize him with the stuff we got out of multi-boot. We stick him in the kernel. This can just go like this. And if I cargo check, I think we can file. Very nice. And maybe what we do now is in our demo, we can, where is it? I lost it. Demo future kernel demo. We can say for y in self.framebuffer.height, and then in 0 to that, for x in 0 self framebuffer width, we framebuffer set pixel. We'll say that we'll set it to like row y column x 1.0 0.0 0.0. So we'll try setting red first and see what happens. We don't have width and height fields on this guy, so we'll just add one. So we'll say pub function height is equal to a u32, and he just returns self.info.height, And we do the same for width. Okay. Cargo run. Okay, so that's concerning. That was a really slow draw. I wonder if we can maybe cargo run release and see if that's any faster. It's possible that doing all of this with floating point math is actually slow enough that we don't want to do it. Let's try again. So in release mode, it's way faster. It's like instant. Okay, so that's fine. I'm okay with that. If it's just like unoptimized code is slow, unoptimized code is slow, no biggie. Okay. And the fact that it's blue is a mistake, right? Let's try this again. So trying to set blue did nothing, and green also is fucked. That's not good. It's possible that the set pixel implementation is fucked up. So let's see. So I'm wondering if it's we had this working before, and we did it by casting to a U32 and shifting. So okay, let's make sure that these offsets are correct. So we'll say print line self.info, and we'll do that when we construct, and we'll make info debug printable. So we'll just say derive debug cargo run. Sure, he doesn't like that because it's not a self struct method yet. So use color size 8, red offset, blue offset, green offset. Oh, these aren't bytes. Oops. So in our multi-boot info, we just have to delete or divide all these by 8. Okay, now it's pink. So we're getting closer. And so green, does RGB with only green make it green? No, that's backwards. So that's a problem. So here we have red map to blue, green map to red, and blue map to green. So I think that if I remember correctly, the offsets are actually backwards for Little Indian, because this is how much I should shift left by. But since I've got these as a U8 array, it's actually backwards. Which means that I have to do self.bytes per pixel. Is it bytes per pixel? Self.info.bytes per pix minus this. Just to like switch from Little Indian to Big Indian ordering. And now all of these guys need to be in brackets. Cargo run. Now I'm just getting nothing, so that's not good. So R still broken, eh? What am I missing? Let's think about this. So we actually we have red offset 0, blue offset 1, green offset 2. So let's confirm, ignoring this red offset field. With Little Indian, oh no, sorry, this should be correct as is, if it's Little Indian, right? Because Little Indian has the smallest byte first. So how could this be wrong? Thinking. Let's just hard code values here first to try. So we'll say adder right volatile 1.0. Oops, this should be like this. We need to keep this offset addition in here. So I'll just say like adder.write the first thing. So the first byte is blue. So it goes B, G, B, G, R, which is just like fucking backwards from what this says, right? We have red offset 0, blue offset 1, green offset 2, but this is, it's not just backwards, it's just like fucking wrong, right? We have B, G, R. Unless our addition is off by 1. Let's see. So we have color size 8. Is that a problem? Color size. Nope, that's fine. Bytes per pixel 4. So that's correct. We have the offset is times bytes per pixel. We have width 640, pitch is massive. Okay. But that's fine. Height is 480. This blue, green, and red offset just seem wrong. And the fact that I've like got scan lines also seems fucked to me. So how can we start debugging? Thinking. It does seem likely that we've got this color info stuff wrong. If framebuffer type is set to 1, it means direct RGB color will be used. Then color type is defined as follows: red, green, blue. Okay, and if I look at the multi-boot info parsing, red gets mapped to red, blue to blue, green to green. And I do in fact see red first, green, blue. Can I look at the address? Like, what if I just, instead of doing this, do self.multiboot info, or I guess it's and self as const-u8, add 110, read volatile. Right? Like, let's just, for my own sanity, I guess I have to cast this as multi-boot info first. And read volatile. Okay, because I know that this is supposed to be at offset 110. That's what it says here. And we'll just manually punch these offsets in, because I'm not confident that these are right. This is R size, R G pause, G size, B pause, B size. Cargo run. So I am getting the same RGB offsets, but they are still just fucking wrong. Why? Why? I don't understand. Unless these, like, field position. Maybe I don't understand what these are. Position. Because I have... Yeah, the fact that it's blue, green, red when it says it should be RGB seems really fucked to me. Can I, like... So how are these guys used? He says he takes he masks it with the mask size, and he shifts it left by the position. And here he has a 32-bit pixel. Whoa. Oh, this is case 24. So he's case 32. So he has the pixel is equal to the frame buffer plus the pitch times I plus 4 times I, where I is what? The width. I is less than frame buffer width, and I is less than frame buffer height? Oh, because he's drawing a diagonal line. Right. So that makes sense. He adds 4 times I. Frame buffer plus... Oh, is the pitch in bytes? That might make this make sense. Oh, no. He has pitch times I plus 4 times I. What is the 4 for? Yeah, it does look like he's not multiplying pitch by bytes per pix. Which would also explain why I have these, like, scan lines happening. I'll make all these use sizes, I guess. That's confusing. But we'll live with it. Okay, cargo run. Okay, so now we've got a solid red screen, so we fixed the scan lining. But we still haven't explained why BGR is backwards. Yeah, that really makes no sense to me. Right? We have red offset 0, blue offset 1, green offset 2, and we're seeing BGR. It just doesn't make sense. Unless I'm, like, off by 1 somewhere really stupid. Right? Like, if I set pixel 0, 0, do I see it? We should probably make the screen smaller so that we can actually see what we're trying to see. So in our multi-boot, in our boot.s, we reduce these numbers even further. So 320 by 240 maybe. All right, it doesn't like 320 by 240. Maybe 640 by 480 is as low as we'll go. It does look like that first byte is valid. And we set... I'm pretty sure I see a small blue pixel in there. And I think I'll find it easier to see a red one. I don't think I see a red pixel in there, actually. Maybe I don't see anything. So maybe I'm off by something. Like, I've got some indexing issue here. I'm just trying to see if I can, like, convince myself. Okay, so I definitely see a green pixel in there. Oh, yeah, you can see it if you pull it out. Okay, so if I add 1, do I see a green pixel? Yeah, there's a green pixel there. And if I had 0, I see a blue pixel there for sure. I know this is bad because on stream you probably can't see. But if I sub 1, do I see anything? No, I don't see anything if I do that. So it does seem like the first byte really is blue. And so I just don't understand what the fuck it's doing. Because their color info, they're doing exactly what I would be doing, right? They're taking the mask and we're shifting it left by the field position, and shifting it left by the field position should be the same as adding in Little Indian. Okay, whatever. I guess we will also, in multi-boot, we will write that these positions don't match expected. Positions do not match reality in QEMUT test. So blue offset we know is the red offset, green is the blue offset, and red is the blue offset. Unexplainable, but we'll come back to that, I guess. That's annoying. Okay. So now let's go back to our test and double check if we can set the whole thing to the color we expect. So we'll say for y in 0.self.framebuffer.height. And this is the same, but for x in width. I missed green in the multi-boot info struct. Oops. Good call. Good call. So it was green offset was 2, which we know is red. So red goes green. Yeah, nice. So we'll do for y, x, we'll try to set it to red, check that this looks right. Run. Okay, that's red. This should be green. Yep. And this should be blue. Okay, so now that's working, but it's very concerning that it's wrong, but whatever. Whatever. Okay. So maybe we can try to draw something now. Stride them and see if the stride matches. Not sure what you mean there. Take the like. No, I'm not sure. I like know what stride means, but I'm not sure what you mean by stride them. Okay, so we've got a way to like see render colors at any pattern that's easy to see. Like, oh, you mean just like, you want to do like x over 3 or something? So we'll say like x, let r is equal to x% 3, or probably y% 3. G is y plus 1% 3, and b is y plus 2% 3, and then we'll say that this is like if this equals 0, then it's valid. And what I'm trying to see is like alternating RGB per row, and then here we can say R as F32, G as F32, B as F32. If this 1.0 else 0.0. I'm just trying to get some nice lines, man. Okay. Cargo run. What have I done wrong here? So I should be seeing alternating RGB. RGB. And I need to punch these in, so RGB. Oops, I should probably only do these once per row. So I'm seeing RBG, RBG, and it does seem like the colors are, like, that's not at all what I expected. Which means that there's something else going on here. Okay. Well, now I'm just confused. So how come if I posted all reds, it was working fine, but if I try to alternate RGB, it's not? I must be doing something fucking stupid. Self row times pitch plus call times bytes per pixel. Line offset. No. It's possible your rights happen to be aligned, so when you write a solid color, it's luck. Yeah, that does seem possible. Seems possible. So what should I print out here to try to, like, debug? In my set pixel, I guess I should write out these offsets that I'm writing to. Or maybe let's try doing only half the pixels and see if that lines up at all. So if I say I only want to write the first half, so we are like in approximately correct, right? Like the fact that we're only writing the first half of the screen when we try to write the first half of the screen indicates something. And if we do the same for height, do we see the top quarter? Yeah, so it's something to do with our color offsets. Why does this change when I resize my screen? I wonder if it's like a QEMU bug. Hey yo, what's up, what's up? So how confusing. It must be something to do with the offsets here. Oh, so I guess, you know what? It's probably the, I've seen this before. So if the bits per pixel is 32, it might expect a write of a U32. And maybe offsetting a little bit into that isn't valid. So maybe what I actually have to do is do what they did before. So we say let color is equal to R as U32 shifted left by 0, let G, or G as U32 shifted left by 8, or B as U32 shifted left by 16. And then we say adder as U32 write volatile color. Cargo check. What's it? Doesn't like something about those shifts. Maybe I need to put brackets around this. Yeah. And cargo run. Nope, still not what I'd expect. So let's just double check if I try to write all red, does it look right again? other than the fact that I'm shifting wrong. So if I try to write all greens, that's working fine. If I try to write all blue or all red, that's working fine. I'm missing something. So clearly, like, the colors are correct to some extent, but writing alternating colors is not. What if I don't try to do line by line? Maybe there's some limit on how frequently the colors can change in the QEMU implementation. So what if I do like y over 4 to try to alternate it less frequently? Okay, so that's working. So maybe there's like some limit on color changing frequency, which would be fucked. But at least would explain this behavior. That's so odd. Very odd. What if I do every 2 lines? That looks good as well. It's just every 1 line that it doesn't like? Like, what the fuck? Oh, maybe this is right, and I just... There's like a... Maybe I just can't see it because it's too hard to see. You could do a gradient from top to bottom and see if the gradient works. That seems pretty reasonable. What's that like? I've seen this like color thing that you put on a texture. I think they call it like mango, RGB mango. No, not what I'm looking for. But I can just set R, G, and B based off of pixel position. So let's do that. We'll say that the red is equal to y as f32 over self.framebuffer height as f32, and g is x, and we'll just do rg0 maybe. There we go. Okay, so that's definitely drawing something. And it looks like correct, other than the fact that we fucked up the colors again. So let's undo what we did in here. Oops. Where did I fuck up these set pixels? Here, I didn't want to do this as color. I wanted to do add self info r red. Hello? What were my values here? Red offset, green offset, and blue offset. So we add red offset right volatile r. And this is green, this is blue, this is G, and this is B. So if this works, I will commit and call that part working. Yeah, I think that is doing exactly what I wanted. And if I swap out red for blue, and I see blue and green, yeah, we're chilling. Okay. So we'll checkpoint here. We'll say rendering colors to frame buffer works. Okay, so here we had a lot of issues with like frame buffer abstraction and color parsing validation. And so now we're at like 139.40. Okay. I guess just to like tie it off, it would be fun to like maybe draw like a bouncing ball or something around the corners, around the edge. And maybe like randomize its color or something as it bounces. So how would we do that? We would put this in a feature. So we'll say let drawing is equal to this. We'll stick this in the list of things that we do. And we have to pin it, or else it won't run. Okay. Then what we can do is we can loop and sleep for like, you know, some amount of time. So we'll say const delta is equal to like 0. Which is gonna be a float. It's gonna be equal to like I don't know, 30 milliseconds. So here we sleep for delta, we take in this monotonic time and the wake up list. We await it and we ampersand these guys. And we have like a position for something that we want to draw. So we'll say that like x is equal to 0.0, y is equal to, or we'll do it in normalized space, 0 to 1. We make a function that's like draw a sphere or something. So it's like a function draw sphere. We'll make it a closure so that it's easier to work with initially. And he's going to take in like a he's going to take in like a position and a radius. Probably we're going to have to clear the frame buffer. So here we're going to set the, we're going to walk the whole frame buffer. And if we're in the sphere, so we'll call this center X and center Y. And we're in the sphere if what? X plus X minus center X squared. Let me think. It's like X squared plus Y squared is equal to radius squared. So for each pixel, we're in the sphere, or in this, I shouldn't call it sphere, I should call it circle. We're in 2D. So this is actually X minus offset squared, Y minus offset squared, I think. Does that make sense? So if I'm at like, if my sphere is at 0.5.5 and I'm at 0.5.5, that sounds right. And this needs to be if we're less than radius squared. Right, because that means that if I'm at like 0.6.5, I'm going to be like 0.1 squared, which should be less than radius squared. Yeah, makes sense. Okay, so we'll say that like X squared is equal to X minus center X, and we multiply by 2, or by itself. And we do the same thing for Y. Yep, you just did an old bad interview question. Yeah, that sounds not a surprise. And then what? If we're in the sphere, if X squared plus Y squared is less than rad times rad, where rad stands for radius, and if in sphere we set the pixel color to like blue or something. Okay. And I guess initially, I just want to test if this works, so we'll try to draw a circle at x, y with a radius 3.1. And we should see something, except there's some mistakes in here. So this should be x as f32. This should be y as f32. And type mismatch. Expected x64. Why? Is this... Okay, yeah, that's why. And then draw... This needs to be mutable, so... which part doesn't it like? Draw a circle needs to be a mutable closure. And if I cargo run, oops, cargo run, do I see a circle drawn? No. So I fucked something up. So print line in sphere. It's in sphere. Let's see. X squared. So if I have x is 0.5, y is 0.5. This should be 0.5 minus 0.5. Oh, oops. This should be x over self frame buffer width. Aha, there we go. Because I was working in like mixing my normalized coordinates and my screen coordinates, or however you want to call it. So just divide these by their width and height because my inputs are in 0 to 1, but these are in pixel space, whatever. These need to be cast to F32s as well. Okay, let's try that now. Oops, these prints are gonna cause all sorts of slowdown, so take those out. Hey, okay, there we go. So now we have a problem where my circle isn't a circle, but it's an oval because I should be like clamping something to 0 to like the smaller of width and height, but I don't really give a shit. Okay, so now what I could do for fun is I could say that every n time I want to draw a circle. So first let's just see if I can keep up by doing that. And maybe at each iteration of the loop, I'll move over a little bit. So we'll do like x plus equals 0.05 or something. Okay, very nice. We forgot to clear in the false case. So here we can set this as 0 to 0. Mr. Bond. Yeah, it did kind of look like the actually, let's take that back up for a second. It does kind of look like that, huh? The like James Bond logo. No, what am I thinking? Is it golden, like the bullet travel intro? I know exactly what you're thinking of. I can't really... Why? Yeah, I don't know how to Google what I'm looking for, but I do... I'm picturing what you said, and... Yeah, anyways. We'll clear in the other case. And now we see it moving. We're definitely not keeping up. Well, maybe we are. Let's see if we reduce our delta. I thought that this should be fast enough that it's fine, but yeah, I think that we're just moving too slow. So probably if we like logged the time here, we would see that the time between frames is longer than delta, but that's okay. And then let's just do one last piece where like we like maybe y also plus equals plus 5, and if we hit the edge, we'll like bounce it off. So how do we do this? We say We'll set a direction. We'll set like a velocity and a y velocity. It's velocity and y velocity here, and then we say if x is greater than if x plus radius is greater than 1.0, we flip x velocity. Let red is 0.1 f32. And we do the same thing for y. Okay. So let's see if we start bouncing off the walls now. Hey! Very nice. Well, except that we forgot to check the 0 side as well. Else if x minus red is less than 0. Or this is just an or. X minus red is less than 0.0. Or y minus red is less than 0.0. Crack a run. Now, the problem is I've accidentally made the DVD logo thing where it hits the corner, except it always hits the corner, except never hits the corner, which is like a big problem. So I guess we can just start by maybe changing its initial position. And now we should see go blomp, 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 blomp. And probably if I like fuck up their velocities a little bit, so it's like non-linear, we might get something. Okay. Well, the frame rate's really fucking low. But that's something. Make it change color every time it hits this corner of the screen. Yeah, that makes sense too. We'll make the radius maybe a little smaller, and maybe that'll help. There we go. And every time it hits the corner, we'll change the color. So we'll just make this a 1.03 initially. And then we'll say for x in what is this? Well, for C in color, maybe we want to do this as like mutable reference color. C is equal to RNG. We have an RNG in here. There's a way to get like we have to lock it, of course. Because it changes its own state, normalized. And we'll do this, we'll change its color on every bounce. Now let's see. Not changing because we have to set the color in the draw circle. So here we pass some color. Here we take in a color. And here we say color 0, color 1, color 2. And color needs to be a F32 3. All right. Boom. Boom, boom. Very nice. All right. So obviously, we're not keeping up, right? If we wanted to render something at like a high frame rate, this would be a fucking disaster, right? Changing every single pixel every time is just taking way too long. So there's something to think about there. You could try to get a little clever and like keep track of where you've written and delete, or probably there's a way to optimize this loop significantly so that it's not so fucking slow. But I think I'm pretty happy with this for now. That was pretty fun. We've proven to ourselves that we can write the frame buffer. There's like lots of stuff in here that is wrong, right? Like the fact that we don't understand why the colors aren't what multi-boot said they were, that's a problem. And we're definitely not handling a bunch of cases here. But I think this is like a kind of fun, nice place to stop for now. So I think probably what I'll do next is I'll probably want to try to figure out how to make it run faster, because like my initial goal here was it would be kind of fun to be able to like write a game of some form. So the next steps would be like handling keyboard input or mouse input, and then trying to use that to like control something on the screen to make like a breakout or Pong or something. But clearly with like the rate that we're rendering right now, that's not possible, and so I'm not really sure what to do next there. So I'll think about that off screen. Thanks for watching. If you enjoyed what you saw, you can always tune back in most days at around 2. Today I started at 1 Pacific time because that kind of like worked better. I might try that again tomorrow. We'll see. So 1 or 2 early afternoon for Pacific time. And if you miss it, there's always YouTube. So if you are in Twitch, there's like YouTube is linked in the description. And if you're watching on YouTube and you want to catch up on, like, peep in on Twitch, say hi, whatever, that'll be linked in the description as well. Thanks for watching. Catch you on the next one. Bye.